So in previous lectures, we have learned how to derive the first order derivative, which is the slope of the tangent line, and the second order derivative, which is how those tangent line changes, how the slope of the tangent line changes, right? So here I'm gonna instruct you to utilize the first order derivative, second order derivative that you have derived to roughly graph a function. Okay, so let's get to it. So first, it's conducive for our understanding by going through all the 7 different possible functional shapes. Okay, the first one is, the first big category is when f prime x is greater than 0. The first order derivative is greater than 0. That actually means y should increase in x. Okay, that is a rough direction that tells you, okay, the function should be from the origin to the northeast, to that area, right? So there is a positive relationship between y and x. When x increases, y should increase. Now the question is, how rapidly should y increase in x? That is told to you by the second order derivative. So if the second order derivative is greater than 0, it is a convex function. Okay. If the second order derivative is smaller than 0, it is a concave function. If the second derivative is equal to 0, it is a linear increasing. So let me demonstrate to you with my document camera. So this is the first case. In which we were discussing f prime x is greater than 0. Okay, so in that case, as we illustrated, the function is roughly going to the northeast, right? As x increases, y should increase. So that's what I mean. So there are actually 3 possible scenarios. This one is linear. Linear means the increasing speed doesn't change, right? The slope is constant, right? Say y equals to 2x. Its first derivative equal to 2, its second derivative equal to 0. So the second derivative in this case equals to 0. Okay, so that's linear case. There is no curvature. So now let's look at the case where it is going this way. Is x and y demonstrating a positive relationship in between? The answer is yes, right? It's still going, the curve is still going to the northeast, okay, from the origin. So now the question is, how is the second order derivative? Well, if you ever get confused, you can pick 2 points, right? When x is small, the slope is pretty flat. When x is big, the slope is getting steeper, right? So that means f prime x increases in x. Namely, your second order derivative should be greater than 0. You are accelerating, right? So the speed is increasing. The slope is your speed, right? So the y is increasing in x in a rapidly increasing mode. Originally, mild increase, especially in here, as you can see, and now it is what we call exponential growth. Okay, so this is the case where f double prime x is greater than 0, and we call this shape as a convex shape. Okay, so here, as you can see, after con, it is a V in here. And a convex shape is like a V shape. Okay, the other case is concave. Concave is like a cave. So it is like this way. First, remember, we're talking about the first order derivatives greater than 0, so y should increase in x. The function should go roughly to the northeast. Okay, so here, if we consider a cave or a tunnel like this, so now we are on the left half of the tunnel. So y is increasing in x. So now, how about the trend of the change rate? Well, again, we're picking 2 points. When x is small, the growth is rapid. When x is big, the growth is getting milder and milder. Say if eventually we're heading here, it's almost not increasing anymore, right? So in this case, f prime x decrease in x. That is to say, f double prime x is smaller than 0. Okay, so this is the concave case. Now let's look at the other case, which is f prime x is smaller than 0. What would be the result? Well, f prime x is smaller than 0. Conceptually, we know that indicates that now between x and y, there is a negative relationship. So instead of traveling to northeast, now you're traveling to southeast. Instead of going to the direction of Massachusetts, now you're going to the direction of Florida. Okay. So previously northeast, now southeast. Okay. So we still start from simple. For a linear case, that's this. Say y equals to minus 2x plus 3. What is the first order derivative? Minus 2. What is the second order derivative? 0. Right? Yes, there is a decreasing trend, but this decreasing trend doesn't change. Right? So say the speed is a constant speed. So that is a linear case. So for a linear case, second order derivative equal to 0. So now let's look at a convex case. So previously we say convex is like a V shape. So for the growth, that is the right side of the V shape, you're going up. Now for the decreasing, dictated by f prime x being smaller than 0, now we're looking at the left side. This is a decreasing trend, right? So let's verify. So first, this is convex, and let's verify. Say, previously, it was dropping rapidly, say, dropping at the speed of minus 100. Now, the dropping speed gets milder, say to minus 2, right? So in that case, f prime x still increases in x. It grows from minus 100 to minus 2. That's a growth, right? So that tells you f double prime x is greater than 0, right? So now we're looking at how f prime x increases with that, changes with x, because that's an increase. So the second order derivative is greater than 0. So now let's look at concavity. This is the case of concave. So previously we were looking at increase. So that was the left-hand side of concave. Now we're looking at the dropping because again, f prime x is smaller than 0. So in that case, we should be looking at the right side of the cave, right? So what is that? Well, originally, it was just a start to drop. And then as x increases, we are dropping more significantly. So say previously it was -2 and now it's -100. Again, f prime x, it is decreasing in x. That tells you f double prime x is smaller than 0. Right? So here we have all the possibility, but for the last one, which is f prime x itself equal to 0. What is that? That is a constant function, right? Like fx equal to 2, it has nothing to do with x, right? Y doesn't change with x at all. No matter what your x is, y's value is still 2, right? In this case, f prime x equal to 0, and also double prime x equal to 0. But it is just the first order derivative equal to 0 tells you it is a constant function, horizontally flat. So here we have all the 7 possible scenarios. I'm gonna take a picture of this and add this to my summary note. Okay, and this summarizes all the possibilities. So now let's look at one practice question. So the practice question is a continuation to our previous question. So one of the previous question that we have solved is fx equal to x cubed minus 4x squared minus 9x plus 19. And here, let me just directly invoke the result. So the result is f prime x equal to 3x squared minus 8x plus 9, and f double prime x equal to 6x minus 8. Okay, so now the question is, now we're looking at page 7 of slide 3-3. So now the question is to ask you when x equal to 3, roughly graph this function. Okay, so now first you need to, in order to graph this function around this point, we need to figure out f prime x and f double prime x. So when x equal to 3, f prime x equal to 3 by 3 squared minus 8 by 3 plus 9. So that is 3 by 9, which is 27, minus 24 plus 9. That's 3 plus 9, which is 12. So that's greater than 0. So here we know, as you're talking about this, we know now we're fixating the possibility under this 3. Now we're looking at the second order derivative, f double prime x when x equal to 3. Oh, there is this way. It's when x equal to 3, or while x equal to 3. That is 6 by 3 minus 8, which is 18 minus 8. That is 10, again, greater than 0. So here you see, for the derivative, that the sign really matters. So now, around point 3, here first it is traveling to northeast because first order derivative is greater than 0, and the second order derivative is greater than 0. That is to tell you now we are growing in an increasingly rapid trend. So this is roughly what the function should be around the point x equal to 3. Okay. So here, there's one other thing just to summarize. No matter what the first order derivative is, here, as you can see, if the second order derivative is greater than 0, then the function is a V shape, right? It is just dependent on the first order derivative to tell you which part of the V it is. If it is if the first derivative is greater than 0, you're in the growing part of the V. So you're gonna take the right side, right, which is this. If the first derivative is smaller than 0, it's a decreasing part. right? You're going to take the left-hand side. It is the same to the concavity as well. If the second-order derivative is smaller than 0, it is a cave. Then it's dependent on what the first-order derivative is for us to take into consideration which part of the cave you should be using, right? So for instance, if the first-order derivative is greater than 0, you should be using the growing part, that is the left-hand side of the cave. If the first-order derivative is smaller than 0, you should be using the decreasing part, that's the right side of this cave. Okay, so that's some tips for you to make connection of concavity or convexity to the derivative. So if you ever get confused, just draw a cave and draw it up and see how the tangent line changes, because the second-order derivative is to describe the change of the slope of tangent line.